if things can go wrong, this is definitely the week. So I'll tell you all a funny story in it, and hopefully it may resonate with you. I don't know. So all of you know that I work at Siemens, and we're responsible for the kind of analytical work with Siemens Mobility with regards to with trains. So structural assessments. If we have to do dynamic stuff, I used to do vehicle dynamics before I was in my current jobs. So more of the theoretical work in the office versus, design and CAD work. And depending on the project, we might do the work within the team that I'm part of. Or it could be done by like another Siemens division, like in Vienna or in Graz, Austria, or Krefeld or wherever. So I started my first meeting this morning at 6:30 a.m. And it was with our customer or a supplier that we're having problems with. And fortunately, like I had gotten up like a half hour before that and dealing with kids. So I was like, I should put on my hat. I haven't taken a shower yet. I accidentally left my camera on. So I realized it when I opened it on, but there I am just like I half woken up with my hat on, and they're like, oh, you're comfortable today. So that was how I started my day off. And then I had another discussion with an upset customer that was flat out saying they didn't trust some of the calculations that were done by our colleagues in Vienna, which are very, very good. And I was walking around the house with my laptop and went in my kitchen to get coffee. And I looked out my window, and my swimming pool looked like it was empty. And I was like, what the heck? So I like I go over to the to the window to look further, and it's like 3 or 4 feet low. Like out of the blue, it's like 3 or 4 feet low. In the meantime, this customer is like irate, like, I don't trust your calculations, and I'm trying to calm them down, like explain it. And I'm like, internally, I'm freaking out in my mind. What the hell's going on with the pool? And I go out there to find out that the filter had like split at the seams, and it was like pumping water down the drain. The pump was full on running, and it was just like a fire hose of water going down the drain. I was like, oh my God. Yeah, so it's been a long day.
That is a pretty long day.
Yeah, that was just all before lunch. So then it went downhill from there, unfortunately. So anyway, we're all human, I guess, right? So it looks like we're still missing someone. So I'll move over to share my screen to see where we went off. So this is what we did on Thursday, where I was kind of giving you the overview of where we're trying to get with these field equations of linear isotropic elastostatics. So we have equilibrium, strain displacement, and then Hooke's law, stress strain. So this Hooke's law is just a fancy way of what we already know, which is sigma is equal to EE, elastic modulus, times strain. This is the boundary value problem that we're ultimately going to try to solve. This find our displacement field such that our strain displacement gives us a strain, which when used in our Hooke's law, produces a stress that satisfies equilibrium. Kind of common sense, right? But these people that write this stuff have to write it out so they can get their dissertation out of it a long time ago. And in fact, I don't want to write the wrong name, but where's it? Don't quote me on the spelling, but these field equations were actually discovered by Navier Cauchy, and they're two French engineers, like from the 1800s. They discovered all of this. So if you were studying physics, or if you were studying structural mechanics and civil engineering, this is what you would have learned in undergrad. They wouldn't have saved it for grad school. So Navier Cauchy are the ones that kind of put these engineering field equations together. So in any case, we we talked about deformation and strain, this displacement vector. We talked about these going from undeformed state to a deformed state. And ultimately, we ended up with our number 2 equation here, where our strain field is equal to 1/2 the partial derivative of our displacement field, I with respect to x, or I sub j and j sub I. And then we talked about strain energy and Hooke's law. We didn't quite get to the end of it, to the punchline of this. But ultimately, we talked about this rate of work done on T, on our traction on the boundary of B. Kind of went through this process, and basically left it that says that we have this strain energy density function that exists. And if you remember, what was unique about it is if we take a body that has the same body, and we were to apply 2 different loads to it with the same boundary conditions, the strain energy density function should equal each other. They should be the same. So that's kind of where we left off.
We have some questions about whether the Navier-Cauchy equation is similar to the Navier-Stokes equation.
I think the question was just the same person.
So it's 2 people, Navier and Cauchy. They're 2 names. They're 2 French engineers. Stokes is obviously someone different. So yeah. So Cauchy is a French engineer. So he probably had, and the Euler is obviously a German engineer. So 2 different people naming it. Yep. Okay. Now, I was going to tell you a neat little aside for that, and I don't remember what it was now. It'll come to me. I'll remind you. Okay. So that's where we left off. So we wrote this out here where I kind of said this is our strain energy density function, and I set it equal to this integral Eij Tij dV. So if we kind of kick off with there, and let me maybe start off with writing 3.9, and I'll publish these notes tonight. I think we'll get through this topic tonight. So
Real quick.
Yeah.
Did you publish the previous notes? Because I looked for them, I couldn't find them. I wasn't sure if I was just looking in the wrong place.
I've only been doing it when someone asks.
I mean, I haven't found any of them, so that made me think I was looking in the wrong place.
Oh, okay.
I had the same experience. I haven't seen any.
Okay, so here we go. If we go to, are you able to see my Canvas page?
Yeah.
Okay, so if you go to home, do you see this right here under notes?
No, we see syllabus and references. At least I do. I don't see the notes section.
Really? Oh, you want to know?
It looks like it's not published. Yeah.
It is now. Can you check? What week is this? Like week 6 or something? You don't say anything for that long?
Like before the project, I sent you an email saying I didn't really know where to look to like help better understand the stuff outside class that we're learning in class.
That's what you meant?
What I was getting at is like, I thought you said you were going to post some of it so we could review it again.
Yeah.
But
Yeah, it's posted now.
Okay. So I don't have a NASA logo on my shirt, and I don't have an ego. So you just have to just say something, okay?
Yeah, I see it there too now.
Okay. Yeah, I'm sorry about that.
We just assume we're doing it wrong.
No. Don't assume that. You have to assume everybody's human and everybody makes mistakes. Yeah. Okay. So the claim to fame is the stress energy density function exists. So we've already set that equal to the other, but I'm gonna kind of rewrite it so we're starting off. So we have this integral over body P EIJ TIJ dV. And maybe I didn't say this last time, and hopefully you picked up on this. This dot means first derivative, right? So we're talking about rates here, strain rate. We're not talking about strain. So that's equal to the integral of P with respect to our traction weight density function dV, and this is for all P contained in B. Therefore, we can write that the strain rate times our stress field is equal to the partial of our traction. These are strain energy density function. And we're going to say for all X contained in B. And I'm not going to do this, but this uses the chain rule. To equal partial of W.
Sorry, what did you say W was?
That's the strain energy density function.
Oh yeah, okay, sorry.
EIJ, or we can write it this way, TIJ minus the partial of our strain energy density function, EIJ, times our strain rate is equal to 0. And what we want to note here is that this portion of it is independent of strain rate. Okay. Now this holds this must hold for any EIJ, so for any string rate. Therefore, our stress tensor, EIJ, is equal to partial derivative of our strain energy density function with respect to our strain field. Where, and I don't know if we've said this before, our strain energy density function is a scalar.
Sorry, up above where it's almost out of screen, where you have the partial of the energy density function, you have the W with an E vector as the argument. So is that just the strain vector?
Yeah, it's just a strain vector. Yeah, that could be written. That could just be E.
Oh, okay, it's the same thing.
Yeah. Okay. So okay. So let's give a little Sprott style example that doesn't clarify things, but hopefully it does. He was my advisor, so I can tease him. I still do. So let's say that we have a really vague spring and we apply a force. And we know that our force is equal to kx, right? K being our spring rate and x being our displacement. Our strain energy density function is simply its rate of work, right? 1/2 kx squared. So if we look at this is force, this is distance, this is k. So if we were to integrate this, we're merely just looking at the area under this, right? So we would get partial of our strain energy density function with respect to x is equal to our force. Now we have a little narrative thing to write, and we're almost at the end of this where we're going to get our general Hooke's law, and it'll kind of play out. So we're making an assumption here. An elastic body is one for which the work done by external forces or by external loads is fully recoverable by mechanical work. So stress is equal to derivative of our strain energy density function with respect to strain. And if we want to write this out again, so you have this in your notes, and I'll write comma, strain energy usually hits strain, strain, that's the function. Strain field and stress field. Where so stress energy function times your strain field has to be greater than 0 for all strains. If is equal to 0, then strain is equal to 0. um, oh, I remembered my random story I was going to tell you guys. Do you remember the Palmer minor rule for fatigue, where you're like doing rainflow counting and stuff? Does that sound familiar to you?
Vaguely.
So that's two names, Palmer minor. That's two names. And the interesting thing is one of the fellows was a German guy, and the other one was an English guy in Stanford. And apparently, they both published the same theory like 10 years apart. And they don't know if the guy that did it at Stanford after the fact ripped it off from the first guy. So they gave him the benefit of the doubt because it was like his master's thesis or something. So they ended up just renaming it in all of our textbooks with both of them. Isn't that crazy? I think stuff like that is strange.
What you're saying is I should look for obscure master's theses and copy that, and so I can have my name named after it too.
That's what I'm hearing.
That's exactly what I was thinking.
Absolutely not, because people try that all the time. And in fact, that's the first thing your professor, your advisor will do is start Googling stuff about your stuff and are using Google, what is it?
Scholar.
Google Scholar to try to find stuff. In fact, there was a senior project a few years ago that did something, and I was kind of questioning their MATLAB code, and sure enough, I found it in a thesis from a guy in India, like verbatim. I mean, MATLAB is very like when you write a MATLAB script, it's very, I don't know the better way of saying it, intimate, right? It's very you, right? The way you write subscripts, and like I write theta, like THEA, other people will do something totally different. It's like they didn't change anything. And I was like, come on. Okay. So as we continue here, for stress, which is our Tij, or you could see it as T underscore a linear function of strain exists. So we have a strain energy density function is equal to 1/2, and things are going to start thinking a little bit more real now. Cij, KL. So you're familiar with this, right? E I J E K L. So we've seen this CIJKL EIJ, right? We've seen this notations already. So this CIJKL, you should be in your mind thinking this full stiffness matrix. So this looks like it's the same form as right here, right? It's just a spring, 1/2 kx squared. Our linear material or stiffness modulus is just that. It's a stiffness, just like a spring, no different than a spring. So our strain energy density function is equal to 1/2 that times our strain in EI times our EKL. And for a reminder, C C is a stiffness modulus matrix. And it's, does anyone remember rank what?
Rank 2.
Comes after 3.
4.
Rank 4 tensor. And if we want to see it in its fully wonderful expanded form, C is equal to CIJKL EI and dyadic product EJ dyadic product EK dyadic product EL. So what we get is, and I'm going to mix up the indices. So T, MN. So this is just a different index, MN. It's the same as the TIJ. It's just different indices. So our stress tensor is equal to the partial of our strain energy density function with regards to a strain tensor, so MN matching indices, is equal to 1/2 CIJKL oh, this isn't going to fit. CIJKL times 1/2 Kronecker IM Kronecker JN plus Kronecker IN Kronecker JM close parentheses EKL plus 1/2 Kronecker KM Kronecker LN plus Kronecker KN plus Kronecker LM EIJ close parentheses, and this equals CMN KL EKL. And that whole thing simplifies to TIJ is equal to CIJKL EKL. this is our generalized Hooke's law.
Hey, Professor, would that be Kronecker Kn times Kronecker Lm at the end? On the, or is that plus?
You are correct. Thank you.
Is there an easy explanation for how we got all those Kronecker deltas in there all of a sudden? Is that like after that's just how it differentiates?
It comes from all these dyadic products. Yeah. We already talked about symmetries in the CIJKL, right? Early on.
Yeah.
We won't repeat that. So that's generalized Hooke's law. So we're getting closer. We've got about a page left here to get to the end goal. So C is considered homogeneous if it does not depend on X and C is considered isotropic if there are no preferred directions in the material. And so what would this equation look like? So the way we have it set up right now is the CIJKL, that's the full 81, right? The full 81 non-isotropic material. What would this equation look like if we had an isotropic material?
Just the elastic modulus.
Yeah. Or we could just write C, right?
Yeah, non-matrix C.
Yeah. So in that particular case, we would have what, sigma?
Sigma equals E times epsilon.
Sigma ij, and then what would we have over here? Or we could just write it like that, right? Or you're used to seeing this as same difference. Okay. Now, for this isotropic state, an interesting thing that I don't know if you've probably thought of is principal directions of strain and stress coincide. They go the same direction. And we'll just write out a simple example here. So if we had E1, E2, E3, is equal to, so this matrix I'm writing right now, what would this be called?
Stiffness.
Is this the C matrix that I'm writing, or
Compliance matrix, that's matrix.
it's the compliance matrix? And how can you tell? What are the
Starting with strain on the left.
1 over E.
both correct? Strain's on the left, and it's 1 over E. That term is the inverse. So these kind of nuances are good because as you're doing your graduate studies, whatever they may be, and if they end up being in mechanics and you're reading textbooks written by different authors that use different notations and things like that, it's this type of general behavior is good to notice so you know what you're dealing with. So you don't just trust what's there, that oh, this is not a C matrix that I'm dealing with, so you don't make a mistake like E is equal to C times T, because that wouldn't be the case. So in what I've presented here, sorry. I can hear my composites professor screaming at me for not writing curly braces there. So, this is a principle in this particular case. Principal stress. This is a principal strain. And obviously, this is compliance, or S matrix. So the above, I'm just going to say stuff, implies the following. CIJKL is equal to nu E, so that's Poisson's, over 1 plus nu times 1 plus 2 nu times Kronecker IJ, Kronecker KL, plus elastic modulus over 2, 1 plus Poisson's, Kronecker IK. Plus Kronecker IL, Kronecker JK. Man, is it raining where you folks are? It's pouring where I am.
Yeah, there was thunder earlier.
I don't know, it was
So-
earlier.
Yeah, like 2-3 hours ago.
Man, it's like coming down like crazy right now. My lights just flickered, so hopefully we keep going.
Oh.
So there's a couple interesting things here. So the CIJK is equal to this whole long thing. This guy right here is equal to something. Does anyone know what this is called? Does that look familiar to anyone? You know what that is?
Lambda.
Yeah, but do you know what it is?
The shear. Oh, is one of them the shear modulus?
This one's the shear modulus. This is called Lemay's parameter, and it's a material property. This wasn't something that I picked up in like ME180 or E45. This was a new one, and it's a material property that's available. So let's write these out so we have them. And it helps solve some of these equations because if you don't have like shear modulus, in some particular cases, if you have this lane parameter, you can get around things. So E is obviously elastic modulus. Nu is our Poisson's ratio.
Would you ever see lambda outside composites?
No, this is elasticity. So yeah, you do. It's going to feed into this. We're almost where we need to go. So this lambda is equal to this lane parameter. And nu is shear modulus. And that gets us to our third pillar of our equation, which is isotropic stress strain relation. Sometimes it's called the constitutive model. And it is Tij stress is equal to our lane parameter, Kronecker Ij, EKK plus 2 shear EIJ. This was number 3 on our list. Our third field equation. So obviously this here is the same as this, right? Cijk EKL. It just gives us another way of solving for it with material properties. What was EKK? Do you remember?
Shear strain?
No, I was just meaning what is when you have something with a repeated indice?
It's partial derivative, right?
No, not with column. Let's write it differently. What's E? No.
The principal strain?
It's different. It's equal to the trace, right? Repeated indice. Repeated indices. Implies trace, TR, or does anyone remember what that is?
Now I remember you circling all the diagonals, but I don't remember what it is.
So, yeah, I shouldn't have written it that way. So E, let's write it this way. E is equal to E11, E12. I'm going to erase that matrix below. E21, E2, E23, E3. So we just have this E tensor. I'll just call it, actually, I won't call it underscore. Uh-oh. Things are freezing. We'll just call this EIJ. So let's say that EIJ, and I just say, I want to know EJJ. So EIJ is equal to this. So EJJ is simply equal to E11 plus E22 plus E33. It's the sum of the diagonals. That's all this EKK is. So we take our stress tensor, you sum the principals, and that gets hit with our Kronecker delta. And remember the rules for the Kronecker delta? If I and j are equal, or if I and j are not equal, they're either 0 or 1. So that means this whole term right here either exists or it doesn't. So depending on what you have going on, it may not be contributing to anything. So in this particular case, EKK is the sum of the diagonals. And so if we sum the diagonals and our Kronecker IJ is 1, that means we're dealing with a principal stress, right? Because this term stays. And if the Kronecker is 0, then we're dealing, our stress field is pretty much only going to be shears.
Are you changing the whiteboard right now? Because it's frozen from like 45 seconds ago.
No, I'm not writing anything. I was just circling my mouse around these different terms. So if Kronecker IJ is equal to 0, then TIJ is equal to and because this is shear modulus, that makes this a shear stress, right? And if Kronecker IJ is equal to 1, then TIJ is principal stresses. Because that term stays. Okay. Yeah, this keeps freezing. Okay. Time we have 20 minutes still. Is that right? So summary. field equations. Of linear isotropic elastostatics. One Tij comma j, so that's our partial derivatives, plus rho bi is equal to 0. Remember, this is equilibrium. This is strain is equal to 1/2 partial large displacement field. And this is strain displacement.
Sorry, can you go up to the boxed equation that's just at the top right there real quick? So I see if the Kronecker delta if ij equals 0, then you have shear stress. And if it equals 1, you still have that shear stress term because there's no Kronecker delta term on the shear area. So you'd still have that with your principal stress.
You could,
Stress doesn't
you
have
could, you could. Well, those should be 0.
so it just naturally those would be 0, so you don't need a Kronecker delta on the right.
Because of the isotropic material behavior. And our third, our constitutive model, Tij is equal to lane parameter Kronecker ij ekk plus 2 shear modulus. Whoa. This thing is being weird. Call this stress strain. So this leads to 15 field equations. And we'll write this out again. the basic boundary value problem. Find a displacement field such that our strain displacement give us strains give us a strain field which, when used in our stress strain relationship, provide a stress field that satisfies equilibrium and boundary conditions. Seems straightforward, right? Find a displacement field that will provide a stress field that we can plug into our stress strain relationship to get stresses. And then based on our stresses, we can establish equilibrium. We want boundary conditions, BCSs, so that the solution i.e. stress field, comma, strain field, comma, displacement field exists and is unique. There are 4 fundamental problems of elasticity. And they are: find stress, strain, displacement, such that 1, 2, and 3 are fully satisfied. And these are fancy ways of writing something that is not that exciting. Our displacements are equal to our displacement. I'm going to put a bar over this of x. For x contained on the boundary of B. I have my body and I have my normal and I have my traction bar. So this is basically saying that a stress field within the body is equal to the stress field on the boundary. B, for all of these, that's what it's implying, is that the bulk, whatever's going on in the bulk of the body at a very high level, is equatable to what's going on at the boundary.
What do the bars mean?
I'm using those to represent the boundary. Yeah. For x contained on the boundary B. C is displacement. So actually these.
Is that an alpha or an X in there?
What?
Is that an alpha in the displacement or an X? Is X there?
X. Yeah. Sorry. So take it back. These first two here are with X. So any X within the body. This one here is on the boundary B. So C. It's just, I think this just is writing the obvious. So our tractions, our normals, our displacement fields, that it has to satisfy, we have to be able to show that it works within the volume, we have to be able to show it works anywhere in the volume, and we have to be able to show that it works on the surface. So if you were to take it, if one of those particular cases doesn't work, then, you know, all bets are off, right? And then D, our displacement is equal to U bar yeah.
When you're talking about the boundary, you're using like the partial derivative symbol, like the partial with the B. Is that just a nomenclature for on, like on something, or is there significance to using that partial?
No, I'm really talking about the boundary, the boundary around it. It's not a partial derivative, it's the boundary. So
Yeah, I know it's not a partial derivative. I was just wondering if that like that symbol we usually use for partial derivatives means like on. So if you use that and then next to B for boundary, it means like on the boundary. Or wondering how that's used. I'm not.
yeah.
I think it was like when it's like a volume and you're doing the derivative, then it's going to be the area, and then when it's an area, it's the line, right? Isn't that the
Yeah,
example?
I think you're asking if that symbol always means that you're talking about a boundary. And I don't think it does.
Or basically on. So because you have the
Yeah.
B, so like on boundary. Oh, but you also have the word on. I don't know.
Yeah.
I was confused. Why
No,
would
this
Well, the B is a body, right? And then the
B is the
partial-
body, so this is referring to literally, that's what I'm trying to write here. So if we take this boundary and it is like separated into the boundary of B1. I think previously we wrote this as a lowercase b. So it would, so like B1, the boundary of B1 would, I'm kind of following the profile, but it's really intended to be right on top of the surface. So that's the boundary, you know, part of it. Call this B2. I think we wrote this out before like this. I think if it was a perfect circle, then it would be the circumference would be the boundary. Versus the area. Um, what this is going to be. Yeah, we can write these out, but they're not going to, we don't really need them for anything. T, so you have them, TN, traction on It's on the partial B or on the boundary. Actually, this one is, I didn't finish that on the boundary B. B. And we have, yeah, I think that's probably good. We're not going to use those.
Can you just clarify real quick, Professor, on that last one? There's not supposed to be two ons there, is it? It's supposed to be like, it's not of X, is it? In the traction on the very last one? Okay. Okay.
Yeah, and actually my notes are messed up here. So the C right here is talking about the entire boundary all the way around. So let's clarify this. Sorry for confusing. So we have B here, and this is C contained notation is not good. Let's rewrite. So the A and B are separate theorems with regards to any X contained in B. So these two theorems are with regards to this guy here. So you could have an X here or here or here or here, anywhere within that B, okay? Now let's take the same body and let's say that I'm gonna cut it right here and I'm gonna have a boundary. So this is intended to be right on top of the one that's there. I'm just writing it on it, where this is the boundary of B. So these two are saying that this has to hold true on this boundary of B. And this one is actually B1, 2, 1, 2. And that is when we have the situation of our same body. In this particular case, we cut our boundary into sections. So maybe this one is boundary of B1 and this part right here is boundary of B2. So this has to hold true for the boundaries of B1 or B2. So if we were to partition this again and have 4 boundaries, then it would have to hold true on all of the boundaries. You would have to be able to show that equivalence. So I think we're out of time. I think next time we'll talk about the Betty reciprocal theorem. Let me show you what that is. And then that kind of leads us to the St. Venant's problem, where you ignore stuff at boundary conditions. And I think after that, we just need to do plane stress and plane strain, and then we can start the finite element solution. Yeah, so three more topics: Saint Venant's or Betty reciprocal, Saint Venant's, plane strain, plane stress, and then we'll start finite element. Okay. So yay, day is over, and we didn't lose power. Still full of water, I think. Okay, so I'll go ahead. I think this is a good stopping point for these notes here because it summarizes the boundary value problem. I'll post this in the location that's published now.
Thank you.
Yeah. All right, folks. Well, have a good night.
Thank you, Professor.
I'll see you on Thursday.
Thank you.
You.
Thank
you, Professor.
Bye, thanks.